an AI-enabled apps session. It's on Liquefaction. You are muted currently. I'm not sure if that's intentional.
Okay. Yeah. Can you hear me now?
Yes, we can hear you now.
Okay. Awesome. Thanks, Rebecca. So yeah, I will be talking about liquefaction, privately liquefying blockchain assets. This is a paper that appeared at IEEE Security and Privacy last year. Special thanks to all my collaborators. Basically, every one of them is a part of IC3. So I guess to start, let's think about blockchain accounts. So often in the ecosystem, you'll see everywhere that protocols and applications are assuming that users have full control over their wallets. And what I mean by this is if you look at dApp interfaces, for example, you'll often see when you sign into them, it'll show you what your current balance is in the account that you connected. And there's an underlying assumption here that you control the full balance in your account. And I mean, that seems like a pretty standard assumption. Even when we look at block explorers, we assume that this same address, which is sending all these transactions, in this case, a VB, we assume that VB controls all the assets and is sending all these transactions and is authorizing all of the transactions being sent from this account. And this kind of makes sense. If we think about how transactions happen, we have some private key that will sign a transaction message. And if the private key is associated with an address that has funds in it and the transaction is valid, then it can get included on chain. And so this assumption I'm talking about is that the user controls this key that's producing transactions. And we make this assumption, I think, because if you share your key with anyone else, then the other party can steal all the funds in your account. So private keys are hammered into people's minds that they're not for sharing. And whenever you make a new blockchain account, your wallet software will remind you not to share your private key or your seed phrase with anybody else. And so this kind of reinforces the concept that blockchain accounts are tied to individuals or individual entities. And we call this the single entity address ownership assumption. And we claim that this is pretty pervasive in the blockchain ecosystem. You would assume that when someone asks you to send money to their address, that they or one person controls that whole account. But as we'll show in the paper, that's not necessarily true. So one thing to note is that when the user is signing transactions, the key exists completely off-chain. And this is what enables us to have all sorts of different types of wallets. But what we can do is, rather than the user directly knowing what the key is, we can instead generate and use a key that's what we call is encumbered inside a trusted execution environment application. So rather than the user seeing what the seed phrase is and writing it down, and being able to have that other method of controlling, we're generating a key and locking it within this T application. And rather than a user having the key within their wallet software and signing messages that way, we instead require the user to send the unsigned message to the trusted execution environment application, which is kind of this lockbox that is has integrity but also privacy. So even the person running this application can't view the key. But anyway, let's say we have the user. The user will authenticate to the T application somehow using maybe some other key off-chain. And then the application will spit out a signed message with that key. So the user never learns what the key is, but can still use it as if it were a regular wallet. And so in this case, the user is signing a transaction, and the transaction, just like before, can get included in the blockchain because it's signed with that key. But what's really cool about this architecture is now we can actually have multiple people using the same key. And the T application can enforce different rules based off who is signing. So for example, usually Alice would never share her private key with Bob because then Bob could take all her funds. But let's say instead we had this T application which enforces different rules for Alice, and then later on, Alice introduces some rules for Bob. And so maybe Alice can sign transaction messages, like Ethereum transactions, for example. But maybe Bob can sign other types of messages. So maybe Alice can spend the Ether in the account, but Bob can only spend the DAI tokens in that account. And maybe we can even tweak this application so that Alice doesn't have any ability to spend any of the DAI tokens in the account. So not only does Alice have the assurance that Bob won't spend her wrapped Ether, but Bob has the assurance that Alice isn't going to spend the DAI that was allocated to him. So we can actually like create a bunch of cool applications using this concept. And here's where the term liquefaction actually comes into effect. So here's an example where we have an asset like a DAO token. If you're not familiar with DAOs, it's like a voting collective that uses decentralized smart contracts for determining the outcome of proposals and what the collective should do. So usually there's this DAO token that you can use to vote on these proposals in the DAO. And having control of a DAO token actually grants you two separate capabilities. One of them is the ability to transfer the token to someone else, just like any other ERC20 token. But it also allows you to sign, sometimes off-chain, these voting messages that lets you participate in the governance of that DAO. And what you can do with liquefaction is you can actually privately sell your voting rights without selling the voting token itself. So what I'm saying is, like, imagine having this DAO token in your account and not moving it at all, but still, like, behind the scenes, off-chain, being able to rent out the voting power behind that token without publicly announcing that you're selling it. So this actually enables us to split this DAO token into two separate assets and liquefy the ability to spend voting power on this DAO token. So, and what makes this different from just delegation is that we can use the TE application to actually enforce that Alice, who is allowing her voting power to be rented out, the TE application can enforce that Alice can never override the vote of the person who purchased those votes. So usually if you delegate your voting rights to some other address, you can still override the vote. But in this case, we can design T applications that don't allow you to override. So Bob has the assurance that when he purchases the voting power that Alice won't violate her side of the agreement, basically. And the way we've implemented liquefaction is using an off-chain wallet system. So, and it uses trusted execution environments, TEs, for managing keys. And the way we allow for like these different policies over like who can spend what or who can sign what in this case, we just use smart contracts to do this, and we run it within a TE-based blockchain actually. And these smart contracts determine which signatures can be made with the key and who can make which of those signatures. So yeah, for example, Alice can sign transactions using our implementation. In practice, this is like our implementation's on GitHub, so you can take a look at it. And the fact that we've written it in using just regular Solidity smart contracts makes it pretty easy to use. But we do have to run it on a TE-based blockchain so that the key remains private. You wouldn't be able to deploy these on a public blockchain like Ethereum. Otherwise, someone could just read the key. And so, yeah, the way it works is like this is an example of a really simple policy where we just allow like a so-called owner to sign any message or any EIP 712 like typed data message using an encumbered wallet. And you'll see it's just like a view function. And the difference is like the TE-based blockchain that we deployed this on actually authenticates view calls. So we're using Oasis Sapphire for T-based blockchain, and you can just write these functions that are view functions that so you can sign messages off chain and also without actually spending a transaction. So you can get these messages signed for free, and it will call into the TE and read the smart contract and based on the smart contract's policy, decide which message can be signed and whether you're eligible to sign it in the first place. So in this case, we have two different ones, and it lets you, it returns the signed message, the signature. And what we've been able to do with key encumbrance is extend it to entire accounts. So you can have an asset that's shared among multiple people who have different portions of that asset. So in this case, we've actually written an encumbrance policy for a whole Ethereum transaction for like a single account. So what I mean by that is you can have a single Ethereum address that have multiple sub balances, each separately controlled by different people. And we've designed it using key encumbrance in a way that the parties can't spend each other's funds. So it's like they have their own separate accounts within this Ethereum address. But to any on-chain observer just looking at Ethereum, you wouldn't be able to see that there were multiple people controlling this account. You would only see that this one account is spending transactions, and so that's kind of where the private part of liquefaction comes in, is you can actually create these off-chain agreements in a way that it's very difficult for other observers to know that there's this sharing of the account going on. So pretty cool. We've also developed a bunch of other applications. Liquefaction enables you to basically create tokens that will redeem access to your account in the future. So this is how you would sell locked or unvested tokens that are in your account. So for example, let's say you have tokens that are locked up in some staking protocol, and you are able to communicate that those locked tokens are fairly secure, so like they're not going to lose money or something. You can create a token that will basically give other people control of the tokens that are in your account sometime in the future. So you can basically liquefy these locked tokens that way. You can also do this to DAO tokens. We even showed how you can turn DAO tokens into like this non-voting, like almost like liquid staking for DAO tokens token that represents the target DAO token. Plus, over time, it will automatically rent out the voting power and accumulate some voting bribes under the hood. So basically, we showed how you can create a non-voting DAO token that will just accumulate voting bribes over time that people can just buy and hold on to. No one's actually like deployed this yet. It would be kind of interesting. But also, we don't really want to encourage voting bribery that much. Another thing you can do is you can rent access to in-person events. So like if you have an NFT that allows you to attend an in-person event or something, you can rent the capability of attending that event to your friend without giving them your whole token or having to do some sort of protocol-specific implementation. So that's kind of another neat thing about liquefaction, is it doesn't depend on support of the protocols that it's affecting. So you can create encumbrance policies for protocols that are currently only designed to work for a single account using a private key. We've also come up with a couple other applications. One thing that's was a really like impactful thing is the Constitution DAO back in 2021 raised millions of dollars to try to purchase an original first run copy of the US Constitution at auction. But they ended up losing out to, I think it was like the CEO of a hedge fund or some sort of financial company who won the auction. And people believe that it's because that Constitution DAO's fundraising was completely public. And so everyone knew how much they were going to bid or what their maximum was. With liquefaction, you can actually, if the users use encumbered accounts, they can actually commit funds to a fundraiser without even making a public transaction indicating that they're spending the funds in that way. So that's kind of cool. We also you can also design policies that restrict the acceptance of funds. Usually in blockchains, you cannot you can't say that you don't want to accept a transaction that's being sent to you. You always inherit those funds, which lead to things like dusting attacks. But with liquefaction, you can actually design policies in which you can provably reject funds that were sent to your address and basically make them unspendable. And then another application is because we're using key encumbrance, it kind of operates beyond the blockchain. So it's kind of above all the blockchains. That is kind of the level we're operating at. So we can create accounts on other blockchains that don't support smart contracts and basically turn those into smart contracts by creating this off-chain policy of what happens when funds are sent to that account and how those funds in that account get spent. We've come up with a bunch of other applications in the paper. We have a table listing all the ones that we've thought of. They're covering governance, reputation, privacy, ticketing, provenance, and also cross-chain activity with the overlay smart contracts. So if you want a more detailed view at all the applications, you can take a look at the paper. The table's pretty easy to follow, so take a look at that. And we do have a countermeasure in case you have some application that doesn't want to interact with potentially encumbered accounts, and we call this complete knowledge. And essentially, a proof of complete knowledge is proof that you did not encumber your key because the key was leaked over some insecure channel, meaning that somebody could have read the full key while you were creating this proof. So this is a possible project idea. Besides making an application that uses liquefaction, you could also build out a better prover or verifier for complete knowledge. That's something we're very interested in seeing. There are some caveats to that. I'm sure Andrew can tell you about them, but there's another cool thing that we did was as a demo, it's not currently live right now, but we might revive it sometime soon, is we encumbered a Bored Ape NFT, and you could, for very little, less than $1, you could take control of the ape, and it will actually create an on-chain transaction from the previous owner's account and literally just send you the ape to your encumbered account on-chain. And the policy would be that you can't control the ape yourself, meaning you can't spend it or try to sell it. But you could log into any sort of application that checks whether your account controls an ape. So you could still use the key for signing into dApps and signing messages. So you could get access to a copyright license while you had the ape in your control, and also access to holder-only spaces like the Bored Studio, for example, and play around with it. So you literally become the owner of a Bored Ape. So in conclusion, digital asset ownership will happen off-chain, and sophisticated private digital asset sharing is possible. Liquefaction kind of just shows kind of the landscape of that. And then also on-chain ownership restrictions are not really enforceable because you can delegate access privately, as we've shown, without complete knowledge. Complete knowledge would show that you can't really do that delegation. Awesome. Thank you.